So, starting today's lecture, we'll be talking about general vector spaces. So, this is chapter 4 of our book, okay? And today we'll talk about the real vector spaces. So, these real vector spaces, actually, this is not new to us. Um, we actually did something in chapter 3 and we talked about, remember, we talked about the Rn, the n dimensional spaces. So those spaces are actually um, examples of vector spaces. So today, starting today, we will generalize the concept. Okay, so let us start with this question. What is an axiom? So an axiom or postulate, so this is a statement which we accept to be true, okay? So from this axiom, we construct mathematical system or structure, okay? So if you recall from your Euclidean geometry class, um, there are 5 postulates in that system, okay? The Euclidean geometry. And these postulates, okay, we have these 5 postulates in here. So using these 5 postulates, the whole Euclidean geometry was constructed. Okay, so these statements were stated originally by Euclid, very, very ancient time ago. Okay, so if you change one of these postulates, for example, this postulate number 5, then another geometry will be created. Okay, but we will not deal about this Euclidean geometry. So we'll be talking about vector spaces. Okay, so what do we have so far? Like I said, we have seen vector spaces in chapter 3, but we know them as the um, Euclidean space, or the Rn, or the n-dimensional real space. And in that chapter, we talked about what we call vectors. Okay, so this set are the objects that we studied in that n-dimensional space. I am introducing the word dimension here, or dimensional here, but we will formalize that later in the course. For now, we know that this n-dimensional um, word in here, okay, we can identify that by knowing the number of components in our vector. Okay, so for example, in R3, we know that the vectors will be of the form you have v sub 1, or let's just say x sub 1, x sub 2, and x sub 3. So there are 3 components here: the first component, the second component, and the third component. And all other vectors in R3 have this form. And we say that this R3 is 3-dimensional Euclidean space. Okay, so for now, that's as of this moment, that's what we know about this dimension. Like I said earlier, we will talk about and we will formalize this dimension um, for a vector space. And then we had several binary operations, such as the addition and subtraction. Okay, we also had scalar multiplication. Okay, we had dot products. We even had cross products, but that cross product is only for the R3, or the 3-dimensional Euclidean space. Okay, and these binary operations, we perform them on the objects of the Euclidean space. So we will also have these guys here in the more general sense. Okay, and of course, we had several properties that are satisfied by the objects and the operations in Rn, or the real dimensional Euclidean space. Real n-dimensional Euclidean space. Okay? So what is a vector space? So let V be an arbitrary, non-empty set of objects on which two operations are defined. We have the addition and we have the multiplication by numbers. Okay? So for the addition, we define this to be, if you got two vectors or two objects in the non-empty set V, then U plus B, which is given by this symbol, we call it the sum of U and V. Okay? And then multiplication by numbers, okay? These numbers here, we call them scalars. Okay? So this is defined as follows. If you have an object U from V, and then you get a K, it's a scalar. It's any number. For us, we'll just be using a real number to be a scalar. Okay? Then this guy here, Ku, okay? This guy here, Ku, it's called the scalar multiple of U by K. Okay? So again, you have the addition and you have this multiplication by numbers, or we call it the scalar multiplication. Okay? So we have a vector space V. Suppose this is your vector space V. Actually, not yet a vector space, but a non-empty set of objects. So it's non-empty. You have these objects here. Okay? And then on this set, okay, on this set, we define these two operations, the addition and the scalar multiplication. Okay? So we say that that set V, okay, is a vector space. Okay? So we say that that non-empty set V with two binary operations given by this addition and scalar multiplication, okay, is a vector space if these axioms here are satisfied. So we have 10 axioms here. Okay? If these axioms, okay, are satisfied by that non-empty set V, okay, then we say that V is a vector space. Okay? So what are the axioms? Here we have the first axiom. If U and V are objects in capital V, okay, then this sum here, U plus V, okay, must also be in V. Okay? So you got two objects in V. If you add them using this binary operation here, if you add them, okay, the sum must also be in V. Okay? And then, next axiom, U plus V must be equal to V plus U. So it means that the addition must be commutative. Okay? Also, U plus V plus W, with this grouping here, you add V plus W first before adding U. It should be the same as U plus V plus W, where you add U and V first before adding W. So this is the associativity. Okay? Of course, I did not mention, but here you have U, V, and W. They are objects in V. Okay? So they are objects in V. Fourth axiom, there must be an object in V. We call it the zero. Okay? We call it the zero. So zero in V, okay, such that if you add any object to zero, it must give you the object that is added to zero. Okay? So you have an object zero in V such that for any object u in V, you must have 0 plus u. It's equal to u plus 0, and it must be equal to u. Okay? So we have this object 0 here. Now, the fifth axiom, every time you get a vector u in V, okay, every time you get a vector u in V, then there must be a negative u in V. Okay? And this negative u, we call it, of course, the negative of u, and it satisfies u plus the negative of u. It must be equal to negative u plus u, and it must be equal to 0. So you have any object in V, there must be a negative of that object such that when you add them, you will get the 0 vector. You will get the 0 in V. Okay? So these first 5 axioms, okay, this actually, well, these 4 axioms here, you are familiar with that. Okay? You are familiar with that. In fact, the other axioms also, you are also familiar with that because we have these properties already. Okay? Number 6, axiom number 6. Okay? If you get any scalar k and any object u in V, then ku, okay, the scalar multiple ku must also be in V. Okay? So this 1 and 6 here, this 1 and 6 here, they are related to the binary operations that we defined. Okay? You have in one, you have 2 objects, you can add them. But the axiom 1 tells us that if you add them, the sum must also be in V. For number 6, you got a scalar and an object in V. If you do the scalar multiplication, okay, k as a scalar, u as the object, if you do ku, then that object, ku, must also be in V. Okay? And then we have these properties, 7, 8, and 9. Okay? And actually 10, related to the scalar multiplication. So you have k times u plus v. Okay? So k times u plus v. This must be equal to ku plus kv. Okay? So this is your distributive property. Okay? Distribution of this scalar over the sum of vectors. And then another type of distributive property here. You have 2 scalars, k and m. Okay? Scalars k and m. You can add them. So you have this k plus m. If you multiply the k plus m to the object u, this is the same as ku plus mu. Okay? So this is distribution of this vector u over the sum of scalars. Okay? Number 7 here, it's the distribution of the scalar over the sum of vectors. Okay? Now, take note, in here, the plus in here, this is the binary operation on the set. V. Okay, it's this plus in here. Okay, so this plus in here, it's the addition in the set V. On the other hand, this plus in here that you see in 8 on the left-hand side, okay, this plus in here, it's the addition of scalars. Okay, we will take the set of scalars to be the set of real numbers. And the addition of scalars, we will take it to be the usual addition that we know. Okay, so this guy here, this is just our usual thing in the set of real numbers. On the right-hand side, for 7 and 8, you see this plus in here. Okay, this plus here, and then this plus here. They are the binary operation on the space or on the objects or on the set V. Okay, because from item number 6, okay, from axiom number 6, Ku will be a vector or will be an object in capital V. Kv is also an object in capital V. Therefore, these are objects from capital V. So if you add them, you must have the addition on the vector or on the set V. Same explanation as in this in number 8. You have your Ku and Mu. Ku and Mu are objects in V. So if you add them, you are adding two objects in V. So you must be using the addition in the set V. Okay? Number 9, you have this. You have two scalars K and M, and you have a vector U. On the left-hand side, we multiplied the scalar M to the vector U. And then after getting the object Mu, we multiply this scalar K. Okay? Now, it's the same as the following. You got the two scalars K and M. Okay? You multiply them using the usual multiplication. And by usual, I mean you are on the set of real numbers, you multiply two numbers. So you get this product Km first, and you will get another real number, which means it will be a scalar. So you have the scalar Km, you multiply it to the vector U. Okay? So again, on the left-hand side, you have Mu first. So you have the scalar M multiplied to the vector U. If you multiply them, it will be an object in V. So this guy here will be an object in V. You multiply the scalar K, you will get this product here. And again, this is an object in V. On the right-hand side, you got the two scalars here, and then you multiply them using the usual multiplication. You will get another scalar. That's your Km. You multiply it to the vector U. Okay? To the vector U. And again, this guy here is an object in V. Okay? And then finally, axiom number 10. We have this one. This is a scalar. Okay? You multiply it to U. Okay? So you have this one. It's a scalar. You multiply it to U. You must only get U. Okay? So 1U, it's equal to U. So these are the 10 axioms that must be satisfied by this set V, a non-empty set, defined with defined binary operations, addition and scalar multiplication. Okay? And the objects in V, we will call them vectors. Okay? So these axioms, okay, uh, I think by now they must be intuitive already. Okay, in a sense, you can perform them by heart without thinking them as if they are actually axioms. Why? Because in the first chapter we talked about matrices. Okay, and we had these properties. We had the zero matrix. We have two matrices of the same size. Okay, we add them. Okay, and we will still retain the size. And the addition commutes. Okay, the addition commutes. You have the associativity of addition of matrices. Okay, if you have a matrix in the set of matrices, you can get the negative of that matrix. You have a scalar, you multiply to a matrix, you multiply the scalar to each and every entry in the matrix. Okay? And of course, if you have the scalar 1, you multiply to the matrix, okay? You will still get the original matrix. So these things here, the concept is not new to us. We are just formalizing it. We are just giving them the more general name. And of course, in chapter 3, we have the Rn. And all of these properties here are satisfied. Okay? Because in fact, Rn, they are vector spaces, whatever your n is, as we will see later in the example. Okay? So now, how do we show that a given non-empty set with two binary operations, the addition and the scalar multiplication, is a vector space? Okay? So these are the suggested steps. Okay? First, you have to identify the set V. Okay? You have to know the form of your objects. Okay? And these objects will be the vectors. If you were able to prove that the non-empty set V is a vector space. And then, once you know the objects, you have to identify what the addition and scalar multiplication are. How do you add these objects? How do you do the scalar multiplication? Okay? So you have the non-empty set V. You should know the addition and scalar multiplication. And then you start verifying these 10 axioms. You start with axiom 1 and axiom 6. Okay? Axiom 1 and axiom 6. Axiom 1 here, we call it the closure under addition. Okay? Or the closure of the operation addition. And number 6, this is the closure under scalar multiplication, or the closure of your scalar multiplication operation. So you start with those two axioms. Okay? And once you've verified the two axioms, axiom 1 and axiom 6, you verify the other 8 axioms. Okay? So these are the suggested steps. Okay? Let us look at some examples of vector space. And these examples that I will show you, these are the examples that we will most of the time use all throughout the discussion and also for the remaining part of the course. Let's start with this vector space. We call it the zero vector space. Right? So let V be the set containing of only one object, which we denote by this symbol, and it's the 0. Okay? Then we define the addition and scalar multiplication by this. So 0 plus 0, it must be equal to 0. And for any scalar k, you multiply to 0, you must get 0. Okay? So you only have one element in the set V. Okay? So when you have these two operations, addition and scalar multiplication, you just operate them on the element 0 of the vector space V. So basically, this definition here, okay, already give us, these definitions here already give us the closure of the addition and also of the scalar multiplication. Because, well, if you add two elements from the set V, you will get another element, it's on the set V. But you only have one element in V. So you can only add that element with itself. Okay? And if you add them according to this definition, you will get the 0. And you get the original element, which is also in the set V. Same is true with this definition. Okay? Same is true with this definition. You have the element 0 only in the set V. You get any scalar. If you do the scalar multiplication, you will get the 0, which is the actual element in V. So closure is there. Okay? So axioms 1 and 6 are true, trivially. Okay? And then if you verify all other axioms, okay, they will also be true. Of course, 0 plus 0 is the same as 0 plus 0. So you didn't notice I used the commutative property there. I interchanged the two zeros. Okay? So commutativity. And even if I have, so that's, let me write it here. Axioms 1 and 6, okay? Trivially true by definition. Trivially true by definition. Okay? Axiom 2, you have 0 plus 0. This is equal to 0 plus 0. This is axiom 2. Axiom 3, you have the associativity. You have 0 plus 0 plus 0. This is the same as 0 plus 0 plus 0. This is your associativity. All of them will just be 0. Okay? Axiom 4, you got the 0 vector. And that's it. That's actually the 0 vector. So axiom 4, you have the 0 vector. And that's just your 0 because for any vector u in the set V, 0 plus u equals u plus 0. This is equal to u. And the only choice for your u, it's just your 0. And then again, you will go back to this guy here. Okay? So axiom 4 is also satisfied. Axiom 5. Axiom 5. For any element or for any object u in V, you must have a negative u. So there exists a negative u in V such that u plus negative of u, this is equal to 0. Okay? But then again, there's only one choice of element. That's just your 0. So you will have 0 plus the negative of 0. This is just your 0. Okay? And this negative of 0, because of the closure, okay, by axiom 6, okay, the closure of, of scalar multiplication, negative 0 is also in V, okay? But V contains only the 0. So this negative 0 here, this guy here, it's also your 0. So axiom 5 is satisfied. Okay? And then I'm gonna leave you the rest. Axiom 7, 8, 9, and 10. You just multiply a scalar, you distribute a scalar, you distribute the object 0 on the scalar, all of them will just be 0. So the 10 axioms are satisfied, okay? And therefore, this set here, which contains only this object, 0, there's only one object, okay? It's a vector space. We call it the 0 vector space, okay? In fact, it's the smallest vector space that we know, okay? It's the smallest vector space that we know. Next example, let V be Rn. So V equals Rn, and then we define we define the addition and scalar multiplication as follows. Okay? Since V is just your Rn, in here, U will just denote it by n tuples. Okay? You have U sub 1, U sub 2, until U sub n. And then, if we get the vector V, let's just denote it by V1, V2, until Vn. So Rn must have, so each vector must have n components. Okay? So the addition in Rn, what we do is just we add component-wise. The first component of U should be added to the first component of V. Okay? First component of U should be added to the first component of V. Second component of U should be added to second component of V, and so on and so forth until you're to the nth component of U added to the nth component of V. Okay? And then KU here. So what we do is just multiply this scalar K to each component of U. So you have here KU, it's equal to the vector or to the n tuple with components ku1, ku2, until kun. We call these two guys here our usual operations on Rn. So most of the time, I will not define this. Okay, I will not define this. I'll just say let plus or let the addition be the usual addition, and let the scalar multiplication be the usual scalar multiplication. Okay? So when I say usual, it will be defined via these two guys here. Okay? So we have the objects, we have the operations. So how do we verify the 10 axioms? Let's start with axiom 1. Okay? For axiom 1, we get two objects. Let U be the vector with components u1, u2 until un, and then v with a vector with components v1, v2 until vn. Okay? So notice these two vectors here, they belong to Rn. They have n components. They have n components. So how do we verify the first action, the closure? We said that if we add these two guys here, they must be also in your set Rn. Okay? But what is the condition for an object to belong to Rn? The object must have n components also. And the components must be real numbers. Okay? So in here, I am assuming since U and V belong to Rn, the components must be real numbers. Okay? So these two guys here, they belong to Rn. So if we add them, okay, if we add them, the sum must also have n components, and also the components must be real numbers. Okay? But notice, according to the definition, you have u plus v, that's equal to u1 plus v1, comma, u2 plus v2, comma, until you have un plus vn. Okay? This is by definition. And this has n components. Has n components. Okay? Also, each component, say u1, ui here, and vi here, so they are on the same location, ui and vi. These are real numbers. And we know that if we add these two real numbers, ui plus vi, this will also be a real number. Which means that u plus v, okay, u plus v, it has n components, and the components are real numbers. So, u plus v also belongs to Rn. And that's the closure of addition. Okay? Axiom 6, similar explanation. Axiom 6, let k be any scalar. And then you get a vector u with n components, u1, u2, until un. You get this vector from Rn. Then again, by definition, ku, this is just ku1, ku2, until kun. And again, this has n components, has n components. And also, kui, this is a real number for any component ui. for any component ui of u. So, ku, this is also in Rn. And that's the closure for scalar multiplication. Okay? So those are the first three steps. First step, you identify the vector space, okay, or the set, the non-empty set. You identify, okay, you identify the conditions so that an object will belong to the set. So we said an object U will be in the set Rn if U will have n components and the components must be real numbers. Those are the two conditions for the object. Okay? And then we identified these two operations. This guy here, it's component-wise addition. This guy here, scalar multiplication, you just multiply each component with a scalar. Okay? And then the third step, verify axioms 1 and 6. Closure in the addition, closure in the scalar multiplication. You identify the sum, check if the sum belongs to your set. Okay? Check if this sum belongs to the set. Also, scalar multiplication, check it if it belongs to the set. So that's your step 3. Step 4, you use you verify the other axioms. Okay? And we use all the properties that we know from chapter 3 to verify the other axioms. So again, I'll leave that to you. Okay? So you have 8 axioms left. But again, you can, like I said, you can invoke all the properties that we discussed from chapter 3. So this is the vector space Rn. We call it the Euclidean vector space. Okay? Questions so far? Next, let V, okay? So let V be the set of all infinite sequences of real numbers. Okay? So if U is in the set V, you will have this form. Okay? You will have the form U1, U2, U3, etc., UN, UN plus 1, UN plus 2, etc. You have infinitely many terms here or components here. Okay? So that's the condition, or those are the conditions. Well, the other condition is that these components here must be real numbers. So those conditions must be satisfied by an object so that that object will belong to the set V. Now, we define the addition and scalar multiplication. For the addition, it's component-wise addition again. But this time, of course, you extend this. Okay? You extend there. And for scalar multiplication, you multiply again the components of your U by the scalar K. And again, you continue the processing here. So these two operations here, these are again the usual operations. So if we talk about the infinite sequences of real numbers, and I said define the usual operations, then what I meant is these two guys here. Okay? So we have the definition of addition and scalar multiplication. We can verify that axioms 1 and 6 are satisfied immediately. Okay? By looking at this, very much similar to what we did in the previous example. So u1, u2 until un plus 1, etc. v1, v2, etc. They are all real numbers. So if you added respective components, you will only get real numbers. So u1, v1, it's a real u1 plus v1, it's a real number. u2 plus v2, it's also a real number. And you do that all the way, okay? And you will still get, look at this, you will still get an infinite sequence. So axiom 1 is satisfied. You get u plus v will still be an infinite sequence, so it must belong to v. Same is true with ku. So this will be an infinite sequence here. So ku will also belong to the vector, to the set v. So axioms 1 and 6 are satisfied. For the other axioms, you can again verify them. Okay? So let me just write here axioms 1 and 6. Okay? Both u plus v and kv are, both of them are infinite sequences. Okay? Now, let's get axiom number 4. Let me go back to the list of axioms. Axiom number 4. There must be a 0 in the object, in the set V, okay, such that if you do this, okay, if you do this here, u plus 0, that should be equal to 0 plus u, okay, and both of them must be equal to u for any object u in V. So let me introduce the 0 vector in this set V. And the 0 vector will be obvious. Okay? So I'll write it here. Axiom 4. We take the 0 vector to be the infinite sequences or the infinite sequence of zeros. 0, 0, 0, 0, etc. Okay? So this is an infinite sequence. All the components are 0, still infinite sequence. And this belongs to V. Okay? For any vector u in the set V, let us give a name to this vector u. So this is the sequence u1, u2, until un, until we have un plus 1, until etc. Okay? For any vector u in V, we verify the property. We need to verify this property here. 0 plus u, it must be equal to u plus 0, and it must be equal to the vector u. Okay? But the verification will be easy. You have 0 plus u. So this is just the infinite sequence of zeros, okay? And then you add this to the infinite sequence u1, u2, until you have un plus 1, etc. But according to the definition, we just add component-wise. So this is just what? 0 plus u1, comma, 0 plus u2, comma, etc. You will get 0 plus un, 0 plus un plus 1, etc. But we know 0 here, the zeros here inside this parenthesis, they are just the real number 0. Use here, u1, u2, etc. They are also real numbers. So in here, you just add real numbers. 0 plus u1, the 0 real number plus the real number u1. 0 plus u2, it's the 0 real number plus the real number u2, etc. And you know that any real number added to the 0 real number, you'll just get the real number, the quote-unquote any real number there. So you'll just have here u1, comma, u2, then you will have un, comma, un plus 1, etc. And this is precisely u. Okay? And you can check. I'll just write it here. Check. This is also the same as u plus the 0 vector. Okay? And that's how you verify axiom number 4. You consider, you find an object that will represent the 0 vector in the set V. And once you have a candidate, you verify the property. So the properties are this guy here. Actually, the property is this guy here must be equal to u. This guy here must be equal to u. Okay? So that's how you verify axiom 4. And then for the rest of the axioms, try to verify them yourself. Okay? Questions? So this set here, example number 3, well, technically it's new because we haven't discussed any infinite sequences. Okay? But it's kinda not so new because this is just an extension of your Rn. Okay? So this is not really quote unquote new. Okay? Next example. Let V be the set of all m by n matrices with real entries. Okay? And then we define the addition and scalar multiplication on V by the following. So again, this is the usual operations. If you add two matrices of the same size, you just add component-wise or entry-wise. If you have a scalar k, you multiply it to a matrix M, you just multiply the scalar k to each entry of the matrix. So usual multiplication, scalar multiplication, and usual addition. Now, if M it's equal to n, meaning we are talking about square matrices, we'll simply write this, okay? Capital M with the subscript small n. Okay? Now, this guy here, or this guy here, it only tells you that the entries must be coming in the set of real numbers. If I remove that, since we are only talking about real vector spaces, okay? If I remove this, I'm still using this guy here. Okay? So, you can easily verify axioms, all the axioms actually. If you have two matrices of the same size, in fact, let's consider the matrix, the set of matrices m by n matrices, okay? Which means that if I get a matrix n, this will have components a sub 1, 1, a 1, 2, etc., a 1, n. And then second row, a 2, 1, a 2, 2, until a 2, n. And then you will have the last row, a m1, a m2, until a mn. So these are, this is the form of the m by n matrix. So this is the form of the objects in capital V. Okay? For this example, well, I will only show axiom number 5. So I have shown you how to do axioms 1 and 6. I have shown you how to do axiom 4. Now I will show you how to do axiom 5. So let n be in the set V. When you have an arbitrary object in your set V, you get it, you must find the negative of that object. Okay? So you have to think of another object that will be the candidate for your object. So in here, we got n as the object in V. We will try to find a candidate negative n. And obviously, we will take this negative n to be the matrix. Okay? To be the matrix whose entries are just the negatives of the entries in n. So this will just be negative a1, 1, negative a1, 2, etc. You have negative a1, n, negative a2, 1, negative a2, 2, etc. Negative a2, n, so on. And then you have negative a m1, negative a m2, and then negative a mn. Once you have a candidate, you verify the property. The property is this. So if you add them, you must get the zero object. Okay? Now, in here, once you've proven axiom 4, okay? So I'll write it here. Do axiom 4, okay? The zero vector is, well, the matrix whose entries are all 0, 0, 0, etc. So it's just your zero matrix. So if you add this n and negative n, you must get the zero matrix. But again, we know that it will end up with the zero matrix using all the knowledge that we know from chapter 1. Then you have n plus negative n according to the definition. Okay, according to this definition here, the addition, we just add component wise or entry wise. So you will have here a11 plus negative a11, a12 plus negative a12, until you have a1n plus negative a1n. And you do this all throughout. Okay? am1 plus negative am1, am2 plus negative am2, amn plus negative amn. And you know, negative, you have a11 plus negative a11, that's just your 0. Okay? A11, the aij's, they are all real numbers. So if you have a real number added the negative, you will just get the 0 real number. So you will end up with the 0 matrix here. Okay? So this is your 0 matrix. So that's how you verify axiom 5. You get an arbitrary object in the set, okay? And then you find a candidate for the negative of that object. Once you have a candidate, you add them. And you must get the 0. If you don't get, after adding them, if you didn't get the 0 object, then you have the wrong candidate. Okay? Questions? So up to this point, it seems that everything, this is what we already know. Okay? So later we will see some examples, some new examples. Okay? Or some new spaces or some new sets. Okay? Which we have not used before. We have not used yet before. Okay? And we will prove that these sets with their definition of or with their defined addition and scalar multiplication will be vector spaces. Okay? Let's start with this. Let V be the set of all real valued functions that are defined at each x in the interval negative infinity to plus infinity. So we will use this symbol, capital F, parenthesis, negative infinity, comma, plus infinity, close parenthesis. So now we are considering functions. Let's get two objects in V. They are just functions. So the object in V will be represented by this bold face F. In here, you have the bold face G. Okay? But they are just the functions f of x and f of g respectively. The scalar, the addition on V, so you add f plus g, okay? The addition in V, it's just the addition of functions f of x plus g of x. So on the left-hand side, you added the two objects, f and g. On the right-hand side, you added the two functions, f of x and g of x. Scalar multiplication. So you have a scalar k, you multiply it to f, to the object f. This will be defined as you have your k, scalar k, a real number k, you multiply it to your function f of x. Okay? And these two guys, these are the usual addition and scalar multiplication of functions. So if you've done maybe Sec 4, well, I hope you've done Sec 4, otherwise you will not be here. So you know the addition of functions and scalar multiplication of functions. So it's the same. Okay? You know that if you have two functions, if you added them, you will still get a function. Okay? So at least you have a function after adding them. The additional condition here, when you added the two functions, okay, you will get another function. That function, okay, the new function must also be defined at each x in the interval negative infinity comma plus infinity. Okay? So I will do axiom 1. So let f, this is your f of x, and then let g, this is your g of x, be functions, be objects in V. So these will be functions that are defined at each interval, at each x in the interval negative infinity to plus infinity. Okay? Then for each, say, x sub 0 in the interval negative infinity to plus infinity, okay, both f of x sub 0 and g x of 0 are well defined. Meaning they are just real numbers. Because here we have real valued functions. So if you evaluate a number, you will still get a number, which means you can add them. So you have your f plus g, okay? And you are evaluating at x sub 0. This is just f of x sub 0 plus g of x sub 0. And this is a real number, meaning well-defined. Okay? And therefore, the sum f plus g also belongs to V. So this is axiom 1. Closure of addition. Okay? You also do closure of multiplication. And the line of reasoning will be similar. You get a scalar k, it's just a real number, you get an object f. That will be a function f of x. Then for each x sub 0 in the interval negative infinity to plus infinity, f of x sub 0 will just be another real number. So k, which is just a real number, times your object f, it's just k times f of x sub 0. And that's again a real number. And therefore, the kf belongs to V. Okay? Questions? So, this example number 5, we also know this. Okay? We also know this from your Sec 4. So, if you verify all the properties, okay, or all the axioms, they will be satisfied. Okay? So, try to verify them. Let's go to this next example. Let V be the set of all positive real numbers. Take note of that. Positive real numbers. So if you get the two objects U and V, they will just be the real number U and real number V. Okay? We define the addition as follows. You add the two objects U and V, so U plus V. It will be defined as the product of the real numbers U and V. So in here, you have the boldface U and V, you add them. On the right-hand side, you have this italicized U and V, you multiply them. So the boldface characters, they are objects in V. The italicized characters, they are the real numbers representing the objects. So the addition in V, it's U times V. The scalar multiplication is this. You have a scalar k, you multiply it to the object u. This is defined as you get the real number u, you raise it to power k. Okay? Let's have some examples. Let u be equal to 3. Let v be equal to 5. Okay? Then here, your u plus v, this will be 3 times 5. So this is equal to 15. Understood? Addition of these two objects. So you get the real numbers representing them. You multiply these real numbers. You get a scalar, say, take note, this is for all scalars. Okay? And the set of scalars, they are, it's the set of real numbers. So in here, let's say, let's take the scalar 2. Okay? So for this, you have ku. Our u there, it's 3. So this is 3 to the power 2. This is equal to 9. Suppose our k equals negative 3. In here, we have ku. This will be 3 raised to the negative 3. So this is 1 over 3 to the power 3, and this is 1 over 27. Okay? Understood? So you have the addition of two objects in V. It's the usual multiplication of real numbers. The scalar multiplication, it's actually the exponentiation. Okay? Let's verify axioms 1 and 6. So if U and V are positive real numbers, then their product will also be positive. Then UV is also positive. So UV, so let me use this bold U plus bold V. This is equal to UV, okay? This is greater than 0, which implies that bold U plus bold V, this is in capital V. That's axiom 1. Axiom 6, for any scalar K and any positive number U, U to the K is also positive. So you have the K, scalar K, and then again, let me use boldface U to represent the scalar, or to represent the positive number U. This is just inside the set V. Okay? So axioms 1 and 6 are satisfied. Let us show axioms 4 and 5. Axiom number 4. What will be the candidate for the zero object? We take the zero object to be the scalar 1, or to be the real number 1. Of course, this one here is a positive number. It belongs to V. Okay? So since 1 is positive, 1 for the 0, which is 1, okay, the 0 object, which is just 1, belongs to B. So this will be our candidate. Take note, this is boldface 0, so I'm saying it's an object in V. And this one here, it's the real number 1. For any boldface U in V, okay, let U be the positive real number, be the positive real number, such that the boldface U, this is just your U. Then We want u plus the 0. We want this to be u, correct? But according to the definition of your addition over here, this is just what? U times 1. And this is just u, which is, this is the boldface u. Similarly, you have the boldface 0 plus the vector u, or the object u. This is just 1 times u. And again, this is just u. And this is the boldface u. So the property is satisfied. Properties are satisfied. So the 0 vector is, so the 0 vector is 1. The positive number 1. That's axiom number 4. And then we do axiom number 5. Okay. Axiom number 5. So I'll write this at once or together. Let this boldface u, which is the real number u here, be in V. What will be our negative u? Our negative u, we will take it to be 1 over u. And 1 over u, this is just, again, a positive number. So this one belongs to V. So what do we want to show? If we add these two guys, u and negative u, we must get the 0 vector. But look, boldface u plus negative boldface u, according to the definition, this is just u times 1 over u. But u times its reciprocal, okay? U times its reciprocal, this is just 1. And we proved in axiom number 4 that this one here, it's your 0 vector. Similarly, you have negative u plus the vector u. So by definition, again, this is 1 over u times u. But then again, this is just 1. And this is your vector 0. So axiom 5 is now satisfied. Okay? So I will now let you do the rest of the other actions. Try to verify all the other actions. So for this, we will see that the set containing all ordered pairs of real numbers, okay, with addition and scalar multiplication given by these two guys here is not a vector space, meaning at least one of the axioms that we have listed in this slide is not satisfied. So at least one of them is not satisfied. Okay, so you can verify the other axioms. Okay, so let us see. Um, you have here the set of all ordered pairs of real numbers. So if you got two objects, U and V, U will just be an ordered pair. Okay, so this is U1 and U2. And V is just an ordered pair. So let's write that as V1, V2. And this U1, U2, V1, V2, these are all real numbers. That's what we have in here. Now, we define the addition and scalar multiplication as follows. For the addition, okay, U plus V, we use the usual addition in R2. So meaning, we just add component-wise. So U1 plus V1, comma, U2 plus V2. That will be the sum U plus V. Okay? For the scalar multiplication Ku, if K is a scalar and U is an object in V, okay, Ku will be defined as follows. K will be distributed to U1. So in the first component of Ku, it will be Ku1. However, the second component will just put it as 0. Okay? So the scalar multiplication is defined as Ku equals Ku1, comma, 0. Okay? So for this, you can verify all the axioms and try to check which axiom is not satisfied. Okay? Maybe let us try some of them. Say axiom number 1. Axiom number 1, it's the closure. Okay? But you look at this. U plus V, it's just the usual addition of real numbers. Therefore, this guy here and this guy here, okay, they are both real numbers. Sorry, U plus V, it's just the usual of additions, usual addition in R2, okay, not on real numbers, but in R2 because we are looking at ordered pairs. Okay, so U1 and V1, U1 plus V1, it's a real number. U2 plus V2, it's a real number, which means that this guy here, okay, is an ordered pair. Okay, so axiom 1 can be proven easily. Okay, so since U1 plus V1, comma, U2 plus V2, these are both real numbers, okay? Then U, so okay, U plus V, this is what? U1, comma, U2 plus V1, comma, V2. This is simply U1 plus V1, comma, U2 plus V2. Okay, this is an element of R2. So it's a pair of real numbers. Okay, and therefore, so U plus V, this is an element of the set V. Okay, for axiom 6, okay, For axiom 6, both k, u1, and 0, these are real numbers, okay, for any scalar k. Okay, so you will have k u. This is just k u1, comma 0. That's according to the definition of scalar multiplication. This is an element of R2. Okay, or that ku1 or ku, this is an element of V. So closure of scalar multiplication is also satisfied. Okay, then you verify all the other axiom. Okay, you verify all the other axioms. But when you go to axiom 10, okay, axiom 10. What is axiom 10? Let us go back to the list of axioms here. Axiom 10 is this guy here. You have a scalar 1, you multiply it to an object u in V, okay? Then you will get the object u in V. So you have 1 times this object u, that's equal to u, okay? So let us go back to this as a request. Okay? So what we're going to show is that axiom 10 is not actually satisfied. And once we've done that, then we see that this set here is not a vector space. Okay? So let's take an object from V. Let U with components U1, U2. Okay? Let U be in V. This means that U1 and U2, they are both real numbers. Okay? Then 1, it's a scalar. It's a scalar. If you multiply U in here, according to our definition of scalar multiplication in here, this will just be 1 times U1, comma 0. Okay? And 1, it's a real number, it's a scalar. U1, it's also a real number. 1 times U1, it's just U1. Okay? And of course, the second component here, this is just 0. But notice, this is not your U1, comma U2. Unless your U2 here, it's actually 0. Okay? Okay? So U1, comma U2, it's not the vector, or it's not the ordered pair U1, comma 0, unless, okay, let me write it here, unless U2, that's 0. But what does this mean? If U is an arbitrary object in V, meaning you actually get some U2 which is not 0. This means that if, say, if U2 is not equal to 0, then 1 U, this is not equal to U. Which means that axiom 10 is not satisfied. So axiom 10 is not satisfied. So the set here is not a vector space. Okay? Now, let us look at some properties of vector spaces. Okay? So here, we let V be a vector space. Okay? It means that this V will have some binary operations. Particularly, it will have the addition and the scalar multiplication. Okay? And furthermore, all the 10 axioms are satisfied. So let V be a vector space. Now, if U is in V and K is a scalar, then we have the following properties. First property, the scalar 0 multiplied to U, okay, it's always the 0 vector. Okay? So the scalar 0 multiplied to U, it's always the 0 vector. Now, if you have any scalar K, you multiply it to the 0 vector here, you will also get the 0 vector. Okay? So any scalar K multiplied to the 0 vector, you will get the 0 vector. Now, if you have the scalar -1, okay, you have a scalar -1, you multiply it to the vector U, what you will get is the negative of U. Okay? So you have a scalar -1, you multiply it to U, you will get the negative of U. Which means that if you have any vector, U, you can always get the negative of that if you just multiply your vector to -1. Okay? And finally, we have this. If Ku, okay, if Ku it's equal to the 0 vector, then either K is equal to 0, so either the scalar is 0, or the vector U, it's the 0 vector. Okay? So if Ku equals 0, then either the scalar is 0 or the vector is the 0 vector. Of course, it can be both. Okay? But at least one of them must be the 0 on their set, either the 0 scalar or the 0 vector. Okay? So for the rest of this part, okay, we'll prove two statements here. We'll prove this guy here and also this guy in here. And then I will leave to you this letter B and letter C. Okay? So again, we want to prove letter A. So we start with that U be an object in V. Okay? Then by axiom 6, you have here 0 U is also in V. Okay? And by axiom 5, 0u has a negative, negative in V. Okay? Say, let us write it as negative of 0u. Okay? Okay. So, we know, this is what we know. So, we know, um, that 0 plus 0, this is equal to 0. Okay? In here, so we know that 0 plus 0 equals 0. In here, we have scalars. We have the 0 scalars in here. Okay? So we have the 0 scalars in here. By axiom 8, so again, axiom 8, it's this distributive property here. Okay, it's this distributive property. So by axiom 8, we have 0 plus 0 u. This is equal to 0u plus 0u. Okay? And because of this, 0 plus 0, it's just your 0 here. This is simply 0u. Okay? So again, we know this from the set of real numbers. 0 plus 0, it's just 0. The zeros here, these are the scalar zeros. And then this guy, this here, the equality in here, it's because of axiom 8. On the other hand, the equality in here, it's because of this statement. Okay? Now, this is what we will have. We saw, or we said that there is a negative for the 0u. So what we're going to do is to add the negative of 0u on both sides of the equation. So we will have here 0u plus the negative of 0u. This will be equal to 0u plus 0u plus the negative of 0u. This is just the addition property of equality. Okay? By addition property of equality. What you added on the left must be added on the right to retain the equality. And then, on this left-hand side, on this right-hand side, we will apply axiom number 3. Axiom number 3, the associative property. Okay? Associative property. So in here, by axiom 5, by axiom 3, we will have 0u plus negative of 0u. This will be equal to 0u plus, we change the grouping, 0u plus negative of 0u. Okay? And then, on both of these, this guy here and this guy here, we will apply axiom number 5. Correct? If you add a vector u to its negative, you will get the 0 vector. Okay? So by axiom 5, the left-hand side will just be the 0 vector. The right-hand side, you still have your 0u plus the 0 vector. Okay? So this guy here, it's just the 0 vector. This guy here, it's just the 0 vector. But you still have this 0u. That's why we ended up with this. And then by axiom number 4, we apply it on this part. You add any vector to the 0 vector, you must get the same vector. So this is equal to 0u. And of course, by symmetric property, okay, by symmetric property, we will have 0u equals the 0 vector. So that's the end of the proof. Okay? Questions? So again, we just applied here the axioms. Okay? So for this part here, okay? For this part here, we apply axiom number 5 so that we will just get 0. When you have a vector, you add its negative, you will get your 0 vector. So we have this vector 0u, we add the negative of 0u, it's this guy here. Okay? So this will just be 0, this will just be 0. So we have this. And then this part here, we apply axiom number 4, we'll just get 0u. Okay? So that's the proof for letter A. Let's prove letter D. So proof letter D. Okay? So in here, we let K be a scalar, and U be a vector in V, such that Ku, this is equal to the vector 0. Okay? So Suppose k, this is not equal to 0. So suppose that this guy here is not true. We will show that the vector u must be equal to 0. But this is easy. Why? If k is not equal to 0, it's a scalar, it's a real number, then 1 over k is well defined. The reciprocal is well defined. Take note, k, it's a scalar, it's a real number. We can do this reciprocal thing. Okay? So, by multiplication property of equality, so by multiplication property of equality, we have 1 over k multiplied to ku. This is 1 over k times the 0 vector. Okay? Now, from here, from this, we will use letter B. We skip the proof, okay? We skip the proof, but I'll be asking you to prove that on your own. So I'm just gonna use this. Anyway, we are proving letter D. So we are assuming that we have proven letter B. So 1 over k, it's a scalar. You multiply it to the 0 vector. This is just the 0 vector. Okay? Okay? So by multiplication property of equality, so I'll separate that one. I'll separate this equality here. Okay? So by MPE, we have this. By item B, applied on the right-hand side, applied on the right-hand side. And on the left-hand side, we will apply this. We will apply this number 9. Axiom number 9. We will regroup. Okay? And by axiom 9, and by axiom 9, applied on the left-hand side, applied on the left-hand side, we will have quantity 1 over k times k. This is equal to u. Multiplied to u. This is equal to the 0 vector. But these guys here, these are all real numbers. Oops. 1 over k and k, they are both real numbers. One is the reciprocal of the other. We are assuming k, it's not equal to 0. Okay, we are assuming k, it's not equal to 0. So we can have 1 over k. But 1 over k times k, that's just 1. Okay? Since 1 over k times k, this is just 1, we have 1 times u. This is equal to the 0 vector. By axiom number 10, 1 times u, it's just u. And now we have u equals the 0 vector. Okay? So we have shown that we have this scalar k and u such that ku equals 0 vector. We assumed that k is not equal to 0. We showed the vector u must be equal to 0. Okay? That's just the first part. The second part, suppose this vector u is not equal to 0. Can we show that k is also equal to 0? Of course we can. Of course we can do that. Okay? Now, suppose that the vector u, it's not the 0 vector. Okay? I think I want to be clear on this part. So let me write this more completely. So letter D, we are still in letter D. So let K be a scalar and V or U be a vector in V such that Ku, this is equal to 0, and I'll write the assumption. And the vector U, this is not the 0 vector. So we are assuming first that the vector U now, it's not the 0 vector. We show that K, so we show that K must be equal to the 0 scalar. So to do this, we will prove this by contradiction. Okay? So if we prove this by contradiction, we will assume that what if this guy here it's not equal to 0 with these hard assumptions. Okay? Meaning they cannot be changed. Only this can be changed. Okay? Okay? So suppose otherwise. Suppose otherwise. That is K not equal to 0. Okay? Using the same analogy or using the same arguments as in above, using the same argument, so arguments as in above, okay? One will show, one can find that U will be the 0 vector. But this is a contradiction because it's a hard no. We are assuming U to be not the 0 vector. Okay? This is a contradiction. This is a contradiction. Okay? So we must have K equals 0. Okay? So that's the end of the proof for letter D.